Welcome everyone. We're continuing a French segment of this seminar. It's my pleasure to introduce our next speaker, Julien Duron. He finished his PhD in France, Lyon, and now he's a postdoc in Warsaw with Szymon Turuńczyk's group. He will talk about dense analogues of bounded expansion. The floor is yours.
Thanks for the introduction. So this is a joint work with Jan Drever, Colin Genier, Nicolas Meinman, Michał Filipczuk, and Szymon Turuńczyk. So this group of people and many others, they are interested in a problem that's called model checking, finding model checking algorithms. So how we can state it is the following. Let's say you want an algorithm A. Let's take as input a graph and a formula of some logic. Fine. And so usually it's a closed formula, and you want, so without three variables, and you want to know if G will satisfy phi. So there is you can choose the logic in which you will write your formula. We will be mainly interested in first order logic, but this problem can be stated for any logic, and obviously you won't have efficient algorithm for any for the set of all graphs. So we will search for algorithm in subset of all graphs. And so the first order case is when phi is allowed to quantify only on vertices of the graph. Okay, so what's an example for that? The most common is, I would say, K-independent set, which is the existence of vertices x1, xk, such that there is no edge between them. For any couple aj. So you could ask, yes?
Assume the xi to be distinct also?
Yes. So your logic is always allowed to use the equal symbol, and since we work on graph, we will also use the edge symbol, so the edge relation between two vertices. And so this problem already you cannot solve in FPT time over all graphs, which means, so an obvious solution would be to test all k tuples over your vertices and ask if it's an independent set. So for k independent set, you can solve the problem in time O of n to the k, where n is the number of vertices. But the question is, can you do it in FPT time? So FPT would be O of some function of k times n to some constant. So you can remove the O, it can be inside the function. So we have some function of k times n to the c. And c is an absolute constant. And we can ask this question for model checking in general. So when model checking is solvable in FPT time. Okay. FPT will be some function of the formula that is as input times the number of vertices to some constant. And this is the main question of our talk. And as I said already, k-independent set is not solvable on general graphs in some function of k times n to the c. So we have to restrict ourselves to some special classes of graphs. And a good tool for that is already to understand how problems interact between them when you change the input graphs. So a good example of that, I think, is to take the simplest possible change of a graph, which is probably the complement, and understand how this problem behaves. So let's say if you complement the graph G, you know you are asking if you can find a set of vertices that have pairwise an edge between them. So the equivalent of k independent set is k clique. So if you take a graph G and you replace it with complement, the problem k independent set becomes k clique. And what it means is that whatever the class of graph you are searching for, it should be that its complement is also in the, let's say, set of classes that will satisfy the model checking, the existence of some model checking algorithm. So what we are looking for is a set of classes that is stable for these kind of modifications. So first we need to define a general way of making these modifications. I will talk first about interpretations. So the idea is you take a formula, let's say theta, that is first order, and consider a class C on which you can apply the formula theta. So it's first order and has two free variables. Let's say x and y. So let's say first on the graph, we will define theta of G as the graph with same vertex set. So V of G prime is V of G, and xy is in the edges of G prime when it satisfies with G together with x and y satisfies our formula theta. In our previous example, the formula was the negation of the edge between x and y. And so the initial graph, so the G prime would be the complement of G, taking theta as the negation of an edge. Okay? But this we could do for any first order, and then apply this to a whole class of graph. So theta of the class C, or a set of graph, is simply the set of all G prime of all theta of G. Oops. So again, it would give you, for theta, the negation of an edge, the complement, the class of the complements of the graphs in the initial class. And the intuition is that if D is a class included in some theta of C, and there is a problem that is hard on D, so model checking phi is hard on D, then there will be some formula, depending on theta and phi, that will be hard on the initial class. Some psi, depending on theta and phi, hard on C. The intuition is not too hard. We can take the formula phi that is hard on D, but each edge of D is defined by the realization of theta in a graph of C. So to find psi, you just substitute in phi the relation E by the relation theta. In phi by theta. So what it means is that if a set of class admits some model checking algorithm, it should be stable for these interpretations. Okay. So we'll define soon the transduction that are little augmentations of this operation. But for now, we can really think of interpretation as a very simple way of making hardness reduction from one class to the other. And now we will introduce a more general kind of reduction, but it's not obvious that it gives you an NP hard reduction. Hardness reduction here, it will be AW. So the transduction is a little more complicated process. It goes into 3 steps. So first, we copy our initial graph. We do some K copy of the graph G. Let's go. So we had G. And we allow some copies of G. And our formula will be able to tell if a vertex is the same vertex but in a different copy. So for each vertex V, we can know if V prime is the copy of B. But otherwise, it's a disjunct union of paths. So if this edge is here, we will have this edge. Then we will add a coloring on all vertices. But okay, instead of a coloring, we can simply choose K sets, fixed number. And these sets, they are not of bounded size. So here, we choose in the copy. We can choose the first purple set, then some blue one, and they can intersect. And being blue or being purple is added to the logic. So we got purple, or V, and blue, or V, that are predicates.
So you have one vertex of each color in each of the copies?
No, not necessarily. For example, V. This is one choice. You could have like all your colors in the same copy. Okay. Or these colors, they are really just any set of vertices in the union of the K copies of G. Does it make sense?
The numbers K are the same?
You can choose them the same. Yes. It's like the maximum of what number you would take otherwise.
By K set, you mean set of cardinality K? Or?
It's a finite it's a positive integer.
No, but what is a K set?
K set.
Choose any K
okay.
different sets, sorry, in the copies. And finally, so we took our initial graph, we choose many possible different sets, and the second step is done in a non-deterministic way. That is, this operation will take the set of copies so it takes, the copy, and returns a set of graphs, that is all the graphs you can, all the graphs augmented by here purple and blue that you can obtain by adding the sets. Okay, and finally, we will apply an interpretation on these graphs. So copies, colors, and then interpretation, which means that one graph will potentially give you many different graphs according to the coloring you choose. So let's do some examples. From one class, from one graph G, you can obtain all the semi-induced bipartite in G. What's a semi-induced bipartite subgraph? So this is G, and we say that the graph, the bipartite graph, is semi-induced in G if you can find two sets, and H is the interaction, but only between these two sets. We don't care what happens inside the sets.
So they are disjoint, these two sets?
Yeah, let's say you can take them disjoint now. So H is, so here, the graph G between the purple part and the blue part, semi-induced in but we remove the edges inside each part. Okay, so how can we find all these semi-induced subgraphs using the transduction? Well, so first we have the colorings. So we can color the two parts of the semi-induced graph we want to find. Purple part and one for the blue part. And then you can choose the interpretation theta to be the existence. So we have purple. So theta takes two variables as input, x and y, and it answers if yes or not there is an edge between x and y. So it says if purple of x is true, it asks if purple of x is true, if blue of y is true, and if there is an edge between purple and blue, between x and y. So the only couple that can satisfy this are the ones with x in purple, the one with x in blue, and this one between. So since we want an edge relation, we should make this formula symmetric between x and y to add the other possibility. So blue x and purple of y. And okay, does it make sense?
How do you lose all the other vertices?
Yeah, sorry, indeed. You can take an injustice. Okay. Because you want to obtain a graph in the end. So you want, so the end structure is defined as the structure where x, y is an edge if you have the formula between x and y. Okay, so it depends. If you see it as a logic, as a binary predicate, like you have an order between x and y here, and it should hold wherever it's x and y, or y and x. Yeah.
We didn't use copy here.
So here we didn't use copy. You could have used copy before and just forget about the copy.
What is that? What does it do?
Yeah, I will give you an example soon where we need a copy. But first, a very nice graph we can obtain is the Hamming graph. So here, let's say, so this is G, and again we choose two sets of vertices, A and B. And we would like to obtain the graph between vertices of B, that is the Hamming graph over A. So the Hamming graph of B over A is, so the vertices are B, and D prime is an edge if they differs on only one vertex of A. There is some V, some A in A, and we have B in B prime, and they are twins except on A. So the difference of the neighborhoods is exactly A. Okay. So, well, how would you do a transduction for that? Again, we don't need copies, but we can choose by purple the set B, by blue the set A. Now the formula is just asking for the existence of some vertex A, such that X is A, Y does not is A, and they agree on all the rest of the vertices.
Sorry. With A is just there exists when I so that the symmetric difference is exactly one. That's what you mean.
Yep. Such that, yeah. And now, so we will need this Hamming graph later. That's why I add it. And now for the copy part, I will do some more complicated example. So let's say we have two formulas, phi and psi, that defines equivalence relations. Okay, so quantitative, reflexive, on vertices. On their variables. So it's, they take two variables and they answer if yes or not they are in the same class. And so there are two formulas of first order. You can find an example is what would be a good example? So having the same neighborhood on the set of all vertices being twins, for example, is an equivalence relation. And what we would want to transduce is a graph that is tripartite. So on the one side, we will put the classes of phi. Here the class is non-empty. The same for psi. And in the middle, we will have the refinement of both equivalence relations. So those are the classes of phi, cap, psi. Okay? So to give an example, phi could be the equivalence of the twin relation but over some blue vertices. Psi the equivalence relation over some purple vertices, and the refinement of both will be the equivalence the twin relation over blue and purple vertices. So being twins for both. And so the obvious graph we want to transduce is is the graph of containment. So where you have an edge if this class intersects this class. So here, let's say we have a class P and the class Q. If this is the vertex P cap Q, we want an edge between this vertex and P and this vertex and Q. Okay, so it's really like the intersection. So this graph is some kind of intersection graph between the equivalence classes. Does it make sense? And so typically for this graph, the transduction would select by some color representant for. So first, we would have 3 copies of the initial graph. One that will be used to make the vertices of P, of phi, one for the vertices of the middle, and one for the vertices of the left. And then, using some colors, we would select the representant of classes of phi, the representant of classes of psi, and the representant of the middle classes. And an edge is defined by satisfying the same equivalence relation. So let's say we have vertex x, some vertex x and y in the copies. So here, so we would have x is in the middle. It can be defined. Y on the left. And they have the same class over psi. Okay. So this example is a bit complicated, I agree, but just to give you an idea of the range of possibilities we can have, and in what we will search for, we are looking for classes that are stable for these transductions. So in the end, this graph, for example, cannot be any tripartite graph. We will have some strong constraints, and using them can lead to characterization of some classes. Okay. Any questions?
So, yes. Here you use the colors also just to keep one representant.
Yeah, we just need the representants of classes. Just to define which vertices are those ones. Yes. Okay. So now transductions are defined, and we are searching for classes for sets of classes that are stable for this transduction. So once we define a transduction over some graph, we can define it over a class of graph. So if T is a transduction, then we say that D is transducible from C. Transducible from C if D is included in the union on the graphs of C of the transduction of G. So each graph of each graph of C will give us a set of graphs depending on the colorings. We can take the union for all graphs of C, and we ask if our final class is inside this union. And so to find the model checking algorithm, we know that on a class C, let's say, we know that we cannot interpret the set of all classes, the set of all graphs. So we will look at this more general operation and define monadically stable the set of monadically dependent, sorry, the classes that cannot transduce the class of all graphs. Okay. So the intuition is if you are not monadically dependent, this transduction is giving you some proof that some problem will be hard. Okay. So the main conjecture of this field is that model checking is FPT. On a class C, if and only if C is dependent. We just omit the word monadically. So as soon as you cannot transduce all graphs, there is an algorithm that model checks. And if you can, there is a proof of hardness. So you can state the conjecture for the logic you prefer. And yes. So an example. I'm sorry, it's because you asked the question, but does anyone remember the set of motors of twin widths 4? Because it's a huge set. It's the team of Lyon. Okay. So twin widths 4 is stating that the model checking of an ordered structure, an ordered binary structure, is FPT if and only if it's dependent. It's 4 and 1. So conjecture holds for third binary structures. So in particular graph that you on which you add a total order that is usable by your logic. So for FO, this conjecture is widely open. But there was some there has been some improvement. Some more very general results about it. So there is two directions. First, just need my notes. Okay, let's do it. Here we do. So here we have dependent classes. So we saw that they are the one not transducing all the graphs. Stable classes are classes that do not transduce orders. So you cannot build a total order via transduction of an arbitrary size using a class that is stable. You may have heard of the class mergewidth, or the class of graphs of bounded twin widths. Or clique widths. So those are sets, each of them is a set of classes. So those are the classes that can introduce order, so they are a subset of the dependent classes. Mergewidth is a recently introduced parameter by Dreyer and Duron. Twin width has been introduced in twin width 1 by René and Matrigan Thomasé. And clique width is a very old parameter, I guess, made by Purcell. I don't know. And so you have this arrows of inclusion of sets of classes. And what is known about model checking is that it's solvable on stable classes. So here model checking is FPT. And so it's FPT on sets on classes of bounded liquids, but even the model checking of more general logics like MSO is. And on twin widths and merge widths, there is an algorithm but only if you are given some decomposition of the graph. So another big question of this field is to bypass this given a decomposition. And just to state it, it was the same for clique widths for a long time, and then I think Seymour and Song-Il Oum, they found an equivalent parameter, rank width, that you can actually for which you can actually compute a decomposition. Okay. So now all those classes, they are stable for transduction. All those sets of classes are stable for transductions. But you may have heard of classes for which we have model checking algorithms, and they don't appear in this drawing. For example, bounded tree widths. There is a slight issue with that, is if you take a class of bounded tree widths, it's sparse. It does not have many edges. But we saw that negation is transduction. So if you take a class of bounded tree widths and you negate the edges, you will obtain a very dense class with almost all edges. So this new class cannot have bounded tree widths, which makes that tree width is not stable for transduction. So we could define a sparse transduction. So first, sparse will mean for all this talk KTT subgraph free. So you cannot have a complete bipartite graph for some t. So a sparse transduction takes a class that is any class, but returns you a sparse class. So T or C has to be sparse. So instead of looking for all the classes you can obtain from a given class C, you just look at all the sparse classes you can obtain from C. And now the question about tree widths makes sense again. So, example, if you take any sparse class, transducible from a class of bounded tree widths, so it's T of C, and C has bounded tree widths. It will have bounded tree widths too. So there is parameters, or sets of classes, that are stable for transductions, but only when you look at the sparse graphs. So now we can complete the picture with some knowledge about sparse classes. So, tree widths is a class that is always included in clique widths. You may have heard of path widths. There is a sparse version of twin widths, but it's really defined as classes of bounded twin widths that are sparse. And finally, two classes, bounded expansion and nowhere dense. So all those classes are only closed for sparse transductions. And we have a chain of conclusion, which looks like this. Okay. And so for a long time, the best model checking algorithm known was by Grohl, Schleicher, and Silberts on this nowhere dense obtained in 2017 on these nowhere dense classes. But it used the fact that it's sparse classes, and so the goal would be to find this counterpart algorithm on dependent classes. So an idea when one wants to find an algorithm is to understand what it means to be in such a class, but for dense graphs. So here we have a good equivalent between sparse twin widths and twin widths. That is, twin widths projects to it when you look only at sparse graph. But what's the proper relation between those classes? How could we define that? So that's the goal of the dense analog. Don't worry, I will define what is bounded expansion at some moment. So given a class C that is sparse, what are the possible dense classes? Let's say property that is sparse. What are the dense classes that corresponds to P? we take the property P, well, what we can do is obviously close P by transduction. So the closure is any class that you can obtain by applying a transduction to P. But you could define a way more general class, a set of classes that are, so this is the dense analogue. That is any class such that any transduction, any sparse transduction applied to C belongs to P. So you take, let's give an example. So the most well-known of those classes is the class of bounded triwits, probably. So for triwits, the closure is called structurally bounded triwits. And the question is, what is the dense analog of triwits? So what is the largest set of classes such that none of them transduce a sparse graph that has not bounded triwits?
And this sparse transduction, there is some bound on T, right? And this is a common constant?
So each T will come to some constant. So each T comes with some formula and some value for the copies and the colors. So those are finite. And so when I say bounded triwits, it's any class that has some bound on the triwits. So if you take one of these classes and you apply a transduction that is sparse, you will obtain a new class that has bounded triwits, but the bound depends on the initial bound on the triwits, the formula used, and the K used in the transduction. Yeah. So it may indeed increase the triwits during the process, but only by some bounded amount. So we can close triwits by transduction, but what would be the analog of triwits? So in the drawing, we see that triwits is the smallest subclass that is dense, and above triwits is cliquits here. So what is probable is that cliquits is in the dense analog. It's included in the dense analog of triwits. That is, whatever sparse class you transduce from a class of bounded triwits, bounded liquids will have bounded triwits. Yes.
Maybe it's I don't see it's simple to see why this dense analog contains the closure of the parameter or the property.
Yes. So those classes, it's a good question. Those classes, they are stable for sparse transductions. So let's say you're a class in the closure, you want to prove that you are in the dense analog. So suppose you are not. If you are not in the dense analog, you can transduce a sparse class that is not in P. Okay? So you have, let's say, P prime, where you have some class C in the closure. And from C, you can transduce sparsely a class, let's say G, that is not in P. Okay, but since C is in the closure, you can transduce C. So there exists some class you can find a class C prime in P that gives an information T prime such that your C is in T prime of C prime. Okay, so you get C from this sparse class and the transduction. And then you can apply T. But T is sparse, T is the transduction, the sparse transduction. So T of SP, T index SP of T prime of our initial class C prime is not in P by definition, by assumption. So this means that C prime is in a property P that is not stable for sparse transduction, because this whole transduction here is sparse. Okay? But it's a good question. So one can prove that clique width is in the dense analog. So there is two fun facts. First, clique width is different from the closure. It's larger. So how can you see that? Well, there is the half graphs. It's a class of graphs that has bounded clique widths. So it's those graphs where each vertex is adjacent to each larger vertex on the other side. They are bounded clique widths, and it's easy to transduce an order from them. What do? Well, you look at the neighborhood and you ask for inclusion of the neighborhood of vertices. We'll give you an order on the left side. That means that they are not stable, because stable class are the ones not transducing any order. But these classes of bounded tree widths, they belong to the stable classes, so they cannot transduce any order. So in particular, they cannot transduce the half graph, so they cannot transduce any class of bounded clique widths.
Is it equivalent to transduce an order and transduce a half graph?
Yes, you can go from one to the other. Okay, so you have different. So we have two different classes and a big open conjecture. It's a variant of Cézeux. Is that clique width is the dense analog of tree widths. is, if you take any class of unbounded clique widths, you can transduce a sparse class that has unbounded tree widths. But this is widely open. It's even open for MSO transduction. So, yeah. Okay. So our goal here is, as the title says, to understand the dense analog of bounded expansion classes. So, what is a class of bounded expansion? So it's defined in, you can define it in an analogous way as table classes. Is there's a set of classes that are sparse and do not transduce sparsely transduce non-degenerate graph. So it's a double negation. Sorry. So whatever the graph you transduce and that is sparse from a class of bounded expansion, it will have a linear number of edges in any of its subgraphs. So do everyone know what is a degenerate class? So it's really, so bounded expansion is really just the strengthening of degeneracy for transductions. It's the largest class that preserve it. Okay, and this is, those classes, they were a central step in the design of model checking of Noah dense classes. Yeah. There's tons of equivalent definition. So this definition is nice because the dense analog of a class of bounded expansion is simply this one. So you remove the sparse property and you obtain the dense analog of bounded expansion. So we are looking for these graphs, and what we prove is that they have some structure. Which is the neighborhood complexity is linear, and we'll go to that. So any class in dense analog has linear neighborhood complexity. So to define it, neighborhood complexity is the number of different neighborhoods you can have on a set of vertices. So you have a set A, and you ask for any vertex of G, it can be in A, what is its neighborhood in A, and you count it. So it's the size of N of G and A. We are saying that so this is a function of A, and we are asking for the max over any n, integer n, of the max for graphs in our class, and set of vertices of size n of the neighborhood complexity of A in G. So the number of neighborhoods you can do picking vertices of G on our set A that is of size n. So the property is, if you take any class in this dense analog, you can prove that it has linear neighborhood complexity. So there is an absolute constant that bounds this number of neighborhoods. Well, here we don't look at the density, we just count them as C times A. Does it make sense? So here we are proving that NC, so this is NC of n, and what we say is there exists some constant C, absolute, depending on the class, such that NC of n is always at most C times n. So either divide.
So drop this max over.
Ah, yeah, sorry. Yeah, sorry. Yeah, okay. I understand. So you have the time to say some quick words about the proof? Yes. The main argument is that it holds for sparse graphs, for sparse classes. That is, if you have bounded expansion, then you have linear neighborhood complexity. Okay, so our goal is to say that if you take a class of in the dense analog of bounded expansion, you can transduce a sparse class, so a class that is of bounded expansion, and you maintain the number of neighborhoods. So by the contrapositive, by absurd. Anyway. So the idea is assume the opposite. So assume superlinearity. So you will find families of sets A, growing size, and sets of neighborhoods on A in some graphs. So each vertex of B will see some neighbor on A, and they all are different. So no A twins in B. So what we ask is that B is superlinear in A. And then we want to design a transduction, a sparse transduction, that builds a graph that maintains this property. So that sparsely transduce some A prime, B prime with no twins in B prime, and the size of B prime is still superlinear in A prime. Okay, so here B prime and A prime are fixed, but it's for growing sets A. So if you do so, you obtain a class that is sparse, a class of bipartite graphs that is sparse, and with large neighborhood complexity, because you kept the neighborhood complexity from your dense graph. But any bounded expansion class has small neighborhood complexity, and so you obtain a contradiction. So for that, the idea is to use a proof that works on dependent classes. Dependent classes have neighborhood complexity of A at most 10 to the 1 plus epsilon for any epsilon. So this is done by Driver, Bellman, McCarthy, Michał-Piliczuk, and Toronczyk. And the idea is a bit the same. So it was known well before that lower dense classes have almost linear neighborhood complexity, and there is a way of sparsifying classes, still maintaining the neighborhood complexity. And so it lifts the bounds to dependent classes.
How does it work? Is this
All epsilon? For all epsilon.
Okay.
It's the same process. You assume that this bound is false, you sparsify your graph, and you obtain a lower dense class that has more than this as linear neighborhood complexity, and this contradicts known results. So I can briefly, I can explain you the main idea of this proof. What we are doing is basically the same, but there is a loss in the sparsifying neighborhood complexity, and so the big question is, how do you avoid this loss? But it's probably not for today. So what's the idea? So we want first to grab a good sparse class that depends on our initial class. And we saw Hamming graph before, and they are the good class. So the property is if a graph G is dependent, if a class is dependent, then the Hamming graphs you can obtain from C, they are sparse, they are degenerate actually. This is an application of Sauer-Scheler proof that Paul mentioned the other day. The idea is, so if you have bounded VC dimension, your Hamming graph is degenerate by following the Sauer-Scheler proof. And if you are not, you contain any bipartite graph you want in your class, and from that it's easy to transduce the class of all graphs. So, by bounding the VC dimension. Now we have a class of sparse graphs, the Hamming graph, that try to represent these neighborhoods. And they have to do something with the neighborhoods. Unfortunately, it's graphs only on the top part. So this Hamming graph, when you take B and A, they tell you in some way how the neighborhood differs between vertices in B. But what we really want is a bipartite graph between B and A that is sparse and tell you something about the neighborhood. Neighborhoods. So from a Hamming graph, you can build a graph that is what we call sadly a merge graph. So it's a bipartite graph between A and B that try to save the neighborhood as follows. So you pick a vertex A in A. So A is responsible for some edges of the Hamming graph. So to remind you, there is an edge in the Hamming graph. These two vertices differs on exactly one vertex. So maybe these two vertices here, they differ exactly on A. What it means is that one of them sees A and the other don't. And otherwise they are twins. So the merge plus graph is exactly the graph relating this vertex to A. So every vertex. So there is an edge AB, if and only if there exists some B prime such that B and B prime, so n of B differs from n of B prime on A, and A is in the neighborhood of B. So this would be B, and this would be B prime. So given our bipartite graph, we can build this other bipartite graph, and it has the good idea of being sparse also.
Also degenerate.
I am unsure of that. So in the dense analog, yes. Of bounded expansion, yes. In the dependent class case, I am not sure. But we don't need it. We just need that it's a graph that is sparse. So it's a good projection of our initial graph. We have the bipartite graph and we obtain a bipartite sparse graph. And so this is the first property of the merge graph. The second, that it decreases some parameter on neighborhoods. So let's do another graph. This is B, and A, B. And now I can look at the vertex A and its neighborhood in the merge graph. And so this neighborhood, let's call it X, you can look at how it interacts with A. So the bipartite graph XA, you can show it has VC dimension at least one less than the previous VC dimension. So this is in the initial graph. in the initial graph. The point is, by doing so, we obtain the two properties.
Can you repeat that?
Yeah.
What's it?
So you take a vertex A,
Yes.
and you take the set of neighborhoods of A, and you can prove that the bipartite graph between the wall A and X, so it's a sub-bipartite graph of the initial one, there is a parameter that decreases, and it's the VC dimension.
D is the VC dimension of all.
And D was the initial VC dimension.
Yes. Of G?
Yeah. So, yeah, I don't really want to go into what's VC dimension and everything, but there is a parameter that is bounded on dependent classes, and we have an operation that builds a graph in which the neighborhoods have this parameter that decreases. So we could apply this operation again on this bipartite graph XA, have a new merge graph, and this process will finish in at most these steps. There is a process finishing that builds sparse graphs along the way, and each sparse graph has something to tell about the neighborhoods. We don't know yet what, but it's built according to interactions between neighborhoods. So now, the only thing that remains to prove is that if the initial neighborhood complexity was large, we maintain large neighborhood complexity in these merged graphs. The goal is to say the following. One, we will build all possible merge graphs. So it will be a set of some function of D graphs. They are all sparse, so we can take the union and it's still sparse. So it will be a big sparse graph, and what we will have to prove is that the obtained graph has the same neighborhood complexity as the initial graph. Okay, so let's zoom a bit. What happens? So let's do the picture again. You begin with the set A, and we have this very large set B of neighbors, different neighborhoods on A. So the merge graph is a bipartite graph between the two, and we can look at the decomposition of B in the twin classes. This is twin classes on the merge graph. So two vertices here, they have the same neighborhood in the merge graph. In particular, they are in the neighborhood of a single vertex of the bottom, except one class that has no neighbors. This is 1, 2. So the VC dimension of BA over A is at most D minus 1. And then we repeat the operation. So we will look at the merge graph between B1 and A and decompose it into classes. And we'll do the same for B2, for B3.
So what are these?
So those, which one? The purple one?
Purple, yes.
So this will be a twin class. So this, let's say, B2K will be a twin class of BK in the merge graph of BK over A. So there is a little lie in this process, which is this merge graph of B to K over A. It's a subgraph of the initial merge graph. So there is nothing. So let's zoom into BK. We have BK and A. And, well, we know that BK is a twin class over A in the merge graph. So they all see exactly the same vertices. There is a set of vertices here, and they all see the same vertices. Since it's a sparse graph, this set of vertices is different. So this is a complete bipartite. Okay. So we would like to divide now BK into a simpler, into different classes according to a merge graph again. But our problem actually is that when we look at the interaction between BK and this part of A, well, what happens is the Hamming graph is empty. Vertices differ on more than one. So a couple of vertices, B and B prime, they have the bad idea of differing on more than one vertex. Yes. And this will be the case for any pair B prime, basically. So we have no Hamming edges, and so the merged graph is basically empty. And in this case, the idea they introduce is basically so we know that these guys, they differ a lot, and they are not twins. So we can remove vertices from A, one by one, and asking if they make twins in the top class. So you choose a vertex A, and you ask how many twins. So let's say how many Hamming edges are labeled by A. How many pairs? B prime differs exactly on A.
Can you repeat why B and B prime differ a lot?
They differ a lot because you chose a class in the merge graph. Okay, so they all agree on the possible merge neighbors. Okay, and so on this side they can differ, but all in the same way and on other vertices. But otherwise there is nothing to say. Like the merge graph had the full information at the beginning, and if there is no edge, it means that the Hamming graph is empty. It's a bit of a lie, but this is the intuition.
So in your drawing, the A that you took out is outside of this red set. It's actually trivial, no?
Yes. So this guy has initially it has no Hamming edges. So the number of pairs here is 0. And the process is simple. You ask if I am responsible for few having edges, I remove this vertex and I remove the twins. So removing this vertex will merge the guy that differs only on him, because there will be twins now, and we don't want twins. So we will remove one twin each time. And yeah, so otherwise, you're responsible for many having edges, and you keep this vertex. It's a nice vertex for knowing different neighborhoods. So many pairs. Nice, and otherwise we remove. And well, you have two possibilities. Either you will remove all those vertices, either you will stop at some point. And what they prove is if you have sufficiently many different neighborhoods at the beginning, you cannot, you can choose good dichotomy here, and the only possible case is having many pairs each time. So I will just end the idea of the proof here by saying that if each vertex A is responsible for many edges of the Hamming graph, these edges, they are all different, because the edge of the Hamming graph is always labeled by a single vertex at the bottom. Let's have A here, it can be responsible for this edge. This A prime here, it will be responsible for some other edge.
The drawing you're doing now is not in decay.
Yeah, they can be responsible for edges in between parts or edges in the parts. What do you mean?
There's no edges inside the part.
But slowly you remove the vertices here, and you stop when each of them triggers many merges. So when this happens, you stop and you say, I have again many merges, so my merge graph will give me some information.
Yes.
Okay. So yeah. This is the full construction of the sparse graph that they obtain. So you take your initial bipartite graph, you remove vertices that do not trigger enough Hamming edges, you find the merge graph, and you do the operation again. And each merge graph will have so what you can prove is the number of twin classes of neighborhoods in the beginning will be preserved after all these operations in the graph you obtain in the end. And this is the contradiction. So before the conclusion, I can add that here we have this decomposition into twin classes, and it's a typical equivalence relation over sets of vertices being decomposed into twin classes. So here we are playing with several different equivalence relations. The red one, then there will be a purple one that we will define, etc. And the interaction between this relation is the graph we transduced at the beginning. This intersection graph between classes of red and classes of purple, for example. When the classes of purple are intersecting many classes. So, okay, this is just to say that if you want to go to the, not to the dependent class, but to the dense analog of bounded expansion, the main idea is to understand how these different equivalence classes behave one to the other. So I would just like to mention two applications of this result and the main open question about this. So the first corollary is that among sparse classes, among stable classes, sorry, I removed it. The Caesar conjecture holds. So this is not just by our work. It happens that a few months ago, Pilipchuk, Gayarsky, and I think McCarthy. Driver, Gayarsky, and Pilipchuk, sorry, proved that if you have a stable class and you have linear neighborhood complexity, which is the property we obtain, then you can pick, you can take your class, transduce sparsely a class C prime, from which you can again transduce C. So there is some kind of invertible transductions. That means that C prime and C are basically equivalent from these transduction closed properties. And so putting this and the proof that the dense analog have linear complexity together, you obtain that from a class C, either you can do this trick, or you can get some non-bounded expansion class. So from any C, you have either it's equivalent to a sparse class, in the sense that they transduce each other, or that it's not in the dense analog of bounded expansion, so it transduces a sparse non-degenerate graph. So this applies only when C is stable. So what it means is, well, if you have unbounded tree widths, what you say is, well, do I have, am I so complicated that I can transduce like very hard sparse graphs, which obviously have unbounded tree widths, because being non-degenerate is enough to have non-bounded tree widths? Or am I sufficiently simple, so I am equivalent to a sparse class, and this sparse class will have unbounded tree widths? So it's some kind of win-win argument. The second corollary should be that classes of size 2 to the big O of n are stable for transduction. That is, so this means the number of non-isomorphic graphs on n vertices. Okay. So the idea is, well, this transduction, they basically either you are in this case and it's impossible for you to be tiny, or again you will find that you are linear neighborhood complexity, and so in the general case you are not equivalent to a sparse class, but transduction behaves nicely for you. That's the thing. And I will end on the main open question, which is merge widths equal to the dense analog of bounded expansion? And the idea is, if we were able to prove that, then hopefully it would come with some way of decomposing graphs in the dense analog, and so to obtain decomposition from merge widths. So that's all.